Okay, lecture 57, standard enthalpies of formation. Should know those terms. Now, the Hess's law problem that we did was fine for finding the delta H of a reaction from a series of other reactions by adding them up, manipulating them and adding them up. Sometimes you don't have that possibility, so we have a more general form. The reason we do Hess's law is because this form is based on, this type of calculation is based on Hess's law. We don't see it here. Sometimes in class, if there's time, I go through it for the students, but it doesn't really add too much. It's nice to see how Hess's law comes into play here. But what we want to use here right now is the final form. The heat of reaction is equal to the sum of the heats of formation of the products times their coefficients. So we take the heat of formation of each of the products times their coefficients. Then we subtract the sum of the heats of formation of reactants times their coefficients. So that's what we're looking for. Now, you have to be given a table of these species. Sometimes you do enough of these, you start to learn some of them. But you got to make sure that not only do you get the right species from the list, but also the right phase. The heat of formation of liquid water, or liquid H2O, is different than for gaseous H2O. So I've got to be careful. Now NO2 gas, I'm going to just put all the heats of formation below. This kilojoule per mole. And it's positive. They can be positive or negative. A lot of them are negative. That's very common. Water, liquid. And this number is very familiar to me, but so is the one for gas, so I always double check. Gas is, for H2O gas, is minus 241.8. So that makes a big difference. So we have this guy. So these are the heats of formation for the different species. Nitric acid is aqueous, and so be careful of that. You can also have species that are aqueous. They can be solid, liquid, and aqueous, and gas. You know, they're all possibilities. They have to be in the standard state of 25 degrees Celsius and 1 atmosphere, so a lot of them may not form gases, or may not, or liquids or solids, depending on what the species is. But just be careful of the phase. And then I'm going to go back and shouldn't have written that, should have written above, but you can see each of the species has its heat of formation. I'm just going to double check to make sure that they're all right. Get the right sign. That's big. Let me put a plus sign here in front. I often do that when I'm working with them just to make sure that I haven't missed the minus sign. That's kind of a helpful thing when you get through, because it can be either. Okay, so what we do is we take the heats of formation of the products times their coefficients. So we have the heat of formation of nitric acid times 2. So 2 times minus 2. And let me do this out completely, since I think we have enough room here. That 2 is 2 moles. And so this is minus 207.4 kilojoules per mole. So the moles are going to cancel. Then we have 1 mole for NO times 90.29 kilojoules per mole. That's for the products. Minus, you have to sum all of this stuff up. Now there's a negative sign here and a positive sign, so and looks like it's going to be negative overall. Same thing could happen on this side. So if you don't have that negative there, if the whole term here for reactants is negative, it should be positive overall. You need to make sure that you group all the products together, all the reactants together, and then subtract them. Having that bracket in there helps you from making a mistake. Let's see if I can fit everything on here. So we have 3 moles, 33.01. Now the standard heat of formation or standard enthalpy of formation for an element in its standard state is 0. So if we had oxygen gas here, that'd make things a lot easier because it'd just be 0. But none of these, I think I chose them so that none of them would be 0. But that can when you have elements as part of your reaction, that's very helpful. Because then for every element, their heat of formation would be 0. Then you can see that would really simplify things. Okay, so let's do this out. So 207.4 times 2. I'm going to leave actually it's just kilojoules, so that won't be too bad, because the moles cancel for each of these all the way down the line. And then this is plus 90. That also helps too when it's 1 mole. But whether it helps or not, you have to do the calculation. 3, so this is going to be 99.30 kilojoules, I think. And then minus 285.8 kilojoules. All right, everything looks good. And you can see that if I've forgotten to put in the parentheses here at the end, I guess there should be brackets, but if I hadn't grouped all of these together, then it'd look like minus 99 minus 285. It's where students make, it's just in the working on the exam, working fast, they try to take shortcuts, and that's when they really, that's when things really fall apart. So make sure you carry everything through. I know it takes extra time. It's okay. It will help you out. It won't help you out each time, and I think that's what students get kind of frustrated with. So, well, he says do this, and all it did was take up my time. I said, well, if you make a mistake, then all that time was wasted completely. So, see, this is minus and a minus, so that's positive now. It's 324.5 plus 186.5, and we get an answer of minus 138.0 kilojoules. I think I kept track of the significant figures, because we're adding and multiplying all the way through, but I think I got everybody. I think I kept them as they should be. Let's try one more here. And this is what I was talking about with the elements. You have 3 molecules, and they have 3 compounds in 1 element. So we can do this a little quicker now. The heat of reaction is going to be 4 moles for NO. And we just did that one, so we have 90, plus 90.29 kilojoules per mole, plus 6 moles, and that 6 is exact, and it's gas, it's water vapor, so it's not the same as the previous problem. It's minus 241.8 kilojoules per mole. And then we subtract. I'm just going to bring it down here. It's because I was going to do the a shortcut, but let's write everything out. Ammonia is minus 45.9 kilojoules per mole, plus 5 moles, and this is oxygen in gaseous form, so this is 0. So really, this term doesn't even have to be put in there. And on my exam, if you left it off, that'd be perfectly fine by me. I know that you left it off because it's an element and it's 0. And oxygen gas, O2 gas, is present in the table. And if you have to go back and check, and you see O2 gas, not O gas, not just O, that's 249.2. Not ozone, O3, which is 142.7, but O2 gas, and that's oxygen in its most stable form under standard conditions, and that's 0. So we do this out, we have 90.29 times 4. So this is 361.16. And actually we multiplied it, so it should be 361.2 kilojoules plus 6 times 241.8. So this is 1.45 times 10 to the 3rd kilojoules, minus 4 times 45.9, and that's going to be minus a 183.6. These cancel, or these minus and minus is a plus, so 361.2 plus 145 times 10 to the 3rd plus 183.6. And this comes up to be 1.99 times 10 to the 3rd kilojoules. And we've added them, so let's see. have to go, this goes out. Oh yeah, that's fine. And that is the deal.